Good afternoon, everyone. My name is Shazi Shen, and I'm from Nagoya University. Today, I'm going to talk about HumTouch, localization of touch on a cylindrical object. Touch sensors are widely used nowadays. The capacitive touchscreen has been commercialized and can be found in cell phones and touchpads. This kind of sensing method was achieved by a specialized surface structure. Recently, touch sensing method for daily objects is wanted. An example is the Ultra Touch Sensing System, which can be used for rigid objects such as a desktop. Furthermore, there are pressure sensing methods which can detect the touches. Here at left is a method measuring the resistance of conductive rubbers, and at right is a sensing method by measuring the capacitance of conductive fibers. Also, the finger tracking method by camera can be used on objects with trackers on it. Another method named tomography can be used for solid, pliable, and paintable materials. In our study, we are researching a passive sensing method different from the methods mentioned above that can be used on non-specialized servers without surface activation. Here, we are going to introduce a touch sensing method named HumTouch. Let's take a look at this video. In this video, a paper is painted with a semi-conductive ink. 4 electrodes were attached at the corners, and the electrodes were connected to a breadboard with 4 red LEDs. When a finger touches the paper, the LED starts to shine, and by moving the finger, the brightness of the LEDs changes. Here is another example of HumTouch. In this video, we replaced the paper into a granite stone. The stone was also attached by electrodes and a breadboard with LEDs, and it functions normally like the previous video. As you can see, LEDs shine when the finger contacts the surface, and the brightness changes when the finger moved. These are the demonstrations of HumTouch. Now, let's talk about the principle of HumTouch. Nowadays, AC power lines are everywhere in our surroundings that generate electromagnetic waves. Meanwhile, human body contains minerals and other conductive materials that will react with the electromagnetic waves, causing current in the bodies. So, suppose we have a conductive or semiconductive material, and we connect it with electrodes. When a finger touches the surface, the current will leak from the skin into the surface. The electrodes will then detect and record the voltages. This is the principle of HumTouch. Here are the characteristics of HumTouch. Unlike those major methods, such as capacitive method, ultrasonic method, and tomography method, HumTouch does not need surface activation. In other words, HumTouch is a passive sensing method. Also, unlike the ultrasonic method, HumTouch can be used for flexible surface. And HumTouch does not have occlusion since camera is not used. In our previous study, HumTouch was proven available for semiconductive materials such as stone. Granite functions as a touchpad by using HumTouch. HumTouch is also available for non-conductive materials such as paper by using special ink. Gesture recognition and localization were conducted on the hydrogel paint paper. However, HumTouch utilizes the environmental noise that are less replicable, so the localization accuracy was low. HumTouch is still a passive sensing technology with many possibilities. Since the voltage data collected by HumTouch is less replicable, we developed a reliable localization method for HumTouch. The method is based on an organized arrangement of the electrodes on a 2D surface. You can see in the picture, 4 electrodes were placed on the corner, forming a 2D coordinate system. As the touch is closer to an electrode, a larger voltage is recorded. The relationship between the distance and voltage is nonlinear. So, we applied the kernel regression analysis to build a regression model to get the relationship between the distance and voltage. By evaluating this model, the voltage data can then be transferred into the location coordinate with a mean estimate error of 0.88 cm. However, the previous method requires an organized arrangement of electrodes to compute 2D coordinates. Therefore, it cannot be used for 3D objects. In this study, we are proposing a method that can also be used on 3D objects. Here is the material we used in our experiment. We used a wood cylinder with a diameter of 3 cm and length of 30 cm. The cylinder was painted with a semiconductive hydrogel, which is made by PVA, PEG, and GA. The hydrogel is durable and lasts for years, and was painted on the wood cylinder, then dried. This is the experiment setting for electrode. 6 screws were put on the cylinder as electrodes. 3 electrodes were nailed at a degree of 0, 120, and 240 on both sides. And the electrodes were connected to an oscilloscope. Here is the experiment procedure. 5 points with 5 cm interval were marked at the degree of 0, 90, 180, and 270. Therefore, there are 20 points were marked on the cylinder. For each of the 20 points, the contact period was about 1 second, and 7 data sets were recorded. The raw data was pre-processed by a moving average filter with span of 5. The figure at right is an example of the data after the pre-processing. 6 electrodes were used, therefore there are 6 different signals, and the maximum voltage was recorded from each channel. Now, I'm going to introduce the method for localization. This page shows the formula processing the voltage data into inputs of the kernel regression model. Input for kernel regression is a vector of 15 elements. Each element is the difference between 2 voltages recorded by 2 different electrodes, and we normalize this difference by the summation of the 2 voltages. We did not use any information about the arrangement of electrodes. Therefore, the input does not depend on the shape of 3D objects. The kernel regression predicts the actual location by a linear combination of multiple functions, where x is the input, phi tilde, z tilde are the estimates phi and z location, n is the number of sample sets, alpha phi I, alpha z1 are the regression coefficients, and we select the Gaussian kernel for the kernel function. The coefficients alpha phi and alpha z were computed by the following formula, where phi and z are the vectors of actual locations. K is the matrix of kernel function formed by the learning data, and lambda equals 0.001 is the regularization term. Here is the result after applying the leave one out cross radiation. The blue circles are the mean estimate location. Black crosses are the actual locations, and the error bars are the standard deviation. The mean estimate error for 20 points were 0.21 centimeters in the z direction and 26.4 degrees or 0.23 centimeter in the phi direction. I would like to briefly discuss our method and results. The method may be used for other 3D objects in any shape, since the method does not depend on the arrangement of the electrodes. Also, the number of electrodes does not need to be 6. However, the minimum number of electrodes still need to be researched. The size limitation was not tested in our study and has to be studied in the future. Our method is comparable to another touch sensing method, such as electric tomography, that involves mean localization errors of less than 10 mm. I conclude my talk. Previous localization methods of HumTouch was only for 2D surfaces. We proposed a method for 3D shapes. The mean localization error was 0.22 cm for a cylinder. That's all. Thank you for your listening.